Calculating the pH of a strong base solution. So, very similarly to a strong acid solution, our definition of a strong base is a strong electrolyte. So, something that completely dissociates in aqueous solution. So, the equilibrium lies 100% to the right. So, in this case, we have potassium hydroxide, KOHAQ. So, what that actually means is we don't really have a molecular solution of KOHH AQ, we have the potassium cation, which breaks apart from the hydroxide anion. And it's this hydroxide anion component that is the basic component of our solution, the hydroxide ion concentration. Okay. Now you do have to watch out for stoichiometry on this kind of question. Like, for instance, if you had strontium hydroxide or barium hydroxide, for every 1 mole of those metal hydroxides in group 2, they're going to liberate 2 moles of the hydroxide ion. Okay, so what we're looking at here is a molar stoichiometry. For every 1 mole of potassium hydroxide, we're going to liberate 1 mole of the hydroxide ion. And it's that mole of the hydroxide ion that is going to allow us to calculate the concentration of the hydroxide ion and therefore the concentration of hydronium and the pH. Because remember, pH is based on the concentration of the hydronium ion. So our first issue is we only have the mass of the potassium hydroxide and the volume of the solution. So we're going to have to convert mass to moles using molar mass and then use the volume to calculate the concentration. An alternative version of the question, you may be given like a stock solution of potassium hydroxide that's been diluted or something. Okay, so all stoichiometric calculations you already know how to do. Okay, so we're going to have to take this 259 milligrams and convert milligrams to grams. How sneaky. So 1 milligram is, of course, 10 to the power of minus 3 grams. So we converted milligrams to grams. Then we're going to have to calculate the molar mass of potassium hydroxide, which is going to be about 56 and change. 1055 grams is the mass of every 1 mole of potassium hydroxide. So far, so Gen Chem 1, right? We converted milligrams to grams, grams to moles of potassium hydroxide. And because we've already written our mole ratio, we can go ahead and convert moles of potassium hydroxide straight into moles of the hydroxide ion. Why not, right? So we've already got our moles of our hydroxide ion right there. If we just stick that into our calculator and calculate. So milligrams cancel, grams cancel, moles of potassium hydroxide cancel, giving us our moles of hydroxide. So you do have to watch out for that stoichiometry. It's not always going to be 1-to-1. So we end up with about 0.004616 moles of the hydroxide ion. So now we can calculate our concentration. Concentration over, number of moles over volume is going to give us our concentration, right? Concentration, number of moles over the volume. Number of moles will be in moles, obviously, and volume should be in liters to give us molarity, right? Concentration in units of molarity, a chemist's favorite concentration unit. Of course, we can have different concentration units, but that's our default. So we're going to take our number of moles, which we calculate as 0.004616 moles of hydroxide, divide by the volume. Oh no, we were only given milliliters. How cruel. ALEKS is making us work for this one. So again, we're going to have to convert milliliters to liters. 1 milliliter is 10 to the power of minus 3 liters. So that should sort us out. Dimensional analysis is our friend. So now we're going to have concentration in units of moles per liter. Okay, so that should shake out to be 0.02885 molarity or thereabouts. Okay, so that's our concentration of hydroxide. So that is stuff that you already know how to do. The new stuff from Gen Chem 2 then is how to calculate pH. So pH is minus log of the concentration of hydronium. And we don't have the concentration of hydronium. We have the concentration of hydroxide. So there's two essentially the same methods that you can use, both involving the ionic product of water. The first one is knowing the equilibrium constant for water, the autoionization of water, Kw, is the concentration of the hydronium ion times the concentration of the hydroxide ion is always going to equal 1.00 times 10 to the power of minus 14. So if you know the concentration of hydroxide, you can then calculate the concentration of the hydronium ion, and then you can calculate pH. So that's method 1. Okay, so I guess we could just go ahead and do that. So I'm going to rearrange so that my concentration of hydronium is the subject. So that is going to equal my Kw, which is 1.00 times 10 to the power of minus 14. In fact, I'm going to write this out as Kw over concentration of hydroxide, just so we can be abundantly clear about what we've done here. And that is going to be 1 times 10 to the minus 14 over whatever we just calculate the concentration of the hydroxide to be. So it's going to be about that. What does that shake out to be? I don't know. I'm going to have to stick it in my calculator. So that gives me a concentration of hydronium equal to, it should be small, right? 3.501 times 10 to the power of minus 13, because we know there's that inverse relationship between concentration of hydronium and concentration of hydroxide. So if our concentration of hydroxide is relatively high, our concentration of hydronium is going to be pretty low, and vice versa. Okay, so we have calculated that. So now we can go ahead and calculate pH. So pH is going to be minus log of the concentration of hydronium, which we just calculated to be 3.501 times 10 to the power of minus 13, and that will be 12.462. Oh, I said 3 decimal places, I think 460. Okay, so that's the first method, okay? And that comes out with a basic pH, which we would expect pH over 7 for a concentration of hydroxide ions, right? For potassium hydroxide, it should be basic. Method 2 is, instead of using Kw, so use pKw, and remember P is just taking the minus log or something. pKw equals exactly 14, and that is equal to the sum of pH plus pOH. So sometimes this second method is a little bit easier in terms of mathematics. You don't have to type 10 to the power of minus whatever in your calculator. So we can obtain pOH by doing minus log of the concentration of hydronium, because P just means minus log the base 10. One note of caution if you choose to do method 2 instead of method 1 is that you're going to get a number right now for pOH, which, you know, if you weren't paying attention, you could interpret as being your final answer, and it is not. So we got the concentration of hydroxide is 288.5. So my pOH value is going to come out to be about 1.540. Okay, so don't be fooled, right? This is pOH, which is inverse to pH, essentially, right? The bigger the pH, the smaller the pOH, and vice versa. The sum will always add up to 14. So then part 2 then is working out from pKw. So pH is going to be pKw minus pOH that we just calculated. So the math is a lot simpler, okay? But we just have to be cautious. So 14 minus 1.540 is going to give me my value for my pH of 12.46, okay? So we're going to get the same answer from that method. So one of those may be easier for you than the other. You either use the Kw expression to convert concentration of hydroxide to concentration of hydronium and then calculate pH directly from that. That's method 1. Or method 2, you're going to take your concentration of hydroxide, calculate pOH, and then use pKw to calculate pH from pOH. Both methods are exactly equivalent. They're going to get you the same answer.